Well, hello all and welcome back. Our topic today is regional bases with known cross-sections. And this is by far one of the neatest, most visual things that we talk about all year. And again, I'll do my best to show it to you on the screen here, and I'll have more of a 3D version to show you in class tomorrow. So one word that's going to become pretty frequent in our vocabulary this week is the term slice analysis. And basically what I mean by that is if you were to take a figure and cut it in half, okay, take a slice of it and, flip at it and stare at it, what shape would you be looking at? So, a real basic example I could think of was just, candy. Can you think of a candy whose cross sections are circles, rectangles, or triangles? Well, if you look at these Necco wafers, if you were to take a knife, and cut that in half, and you look at the shape that it made, you would be seeing circles. Or if you took a Hershey bar and you cut that in half, you looked at its cross-section or the slice that you cut, hopefully you would be seeing a very thin rectangle. Or this interesting candy here. If you cut that in half, the slice that you would be looking at, or the cross-section, or known as slice analysis, would be a triangle. So the idea of these regional bases with known cross-sections is a little different from what we've been doing. We're not going to revolve or rotate our section around anything. Basically, what we're going to do is we're going to take our flat section here, and you can see that circle I have, x squared plus y squared for values that are less than 1, and we're going to put a known cross-section in there. For example, in this shape, I have a square. I certainly can build a triangle in here, a hexagon, a semicircle. I could put any shape I want in there. But again, we're not rotating. I want to be very clear on this. We are not rotating or revolving here. We are basically just taking a shape and putting it inside of our figure here. Now, our goal is to put an infinite amount of these shapes in here. So I want you to try to picture this, and again, I know it's hard on this two-dimensional surface here, and I'll have a better example in class, but I'm going to put another rectangle, another square here. Okay, and again, because it's a square, its base would have to be the same as its height. And obviously, as you got closer, would you agree these squares would be getting very, very small? The closer you got to the end here, the smaller the square would be. Now again, try to picture putting an infinite amount of squares in there. I would hopefully say you would have the largest square in the center. And again, all the bases and heights would be equal. And as you got closer to the end here, you would have a smaller square. And here's what I picture that to look like. I think you would end up with something that looks like this. And again, hopefully you can see my squares in there. I've got the largest square in the center, and again, they get smaller and smaller as they meet at the end. And you're going to get this really neat shape. You can kind of see what it looks like here. And this cross section, so what these squares are going to get us when we put them in the circle, is this shape like this. And our goal is to find the volume of that figure. And here I've got one more picture for you. I tried to put more squares in it so it became a little more obvious to you. Again, you can see the squares getting smaller, but take note that obviously it's a square. The base and height should be equal on each one of these squares. All right, so here's how we're going to attack this mathematically. We're given f of x equals 2x and g of x equals 4x minus x squared. And what we want to do is we're going to graph that real quickly. So 2x, obviously just a line, slope of 0, goes through 0, slope of 2. If I factor this, I can plot an x, 4 minus x, tee it up. This one should be crossing at 0 and 4. And it's upside down parabola, of course. Looks like this. So for part A here, what I want to do is I want to find the volume when I fill this figure with squares. And again, I will have more 3D, models to show you in class, but my goal is to fill this with squares. So here's what's happening. I'm basically taking and I'm building out this, I'm going to try to draw it the best I can here, building out this 3D, it's pretty bad, shape here. And every place I'm going to build a square, build a square, build a square. So you got to picture it coming out at you. It's going to be smaller as it gets close to where they intersect and largest here in the center. But you've got to picture this 3D square coming up at you. So here's how our slice analysis works. And let's go ahead and make sure you jot that down in your notebook. Every AP teacher in the country is going to use the same terminology here. We're going to call this a slice analysis. And basically you're saying, if you can find the area of one of these squares, okay, so I want the area of one square, and then I'm going to add up all the squares that fit in there. So basically I'm going to integrate from A to B the area of that one square. And that will get me the total volume of the shape. All right, so again, that's what we've been talking about all year with integrals. You find the area of one, and then you add them all up, integrating, to get the total volume. So here's how my slice analysis is going to work. I'm always going to start with the area formula for the shape I chose. So in this case, I chose a square, so hopefully you're saying the area formula is base times height. Now, of course, that formula is going to change every time your shape changes. So I identify my formula and I say, okay, I need a base and I need a height. So if I look in this picture, my base is going to be upper minus lower. Let me just grab a different color to stress that. Upper minus lower. That's where the base of my my square is sitting. So my base is going to be 4x minus x squared minus my lower, which is the 2x. Now what's handy is because it's a square, my height is also going to be 4x minus x squared minus 2x. Okay, now I need my area, and my area formula is just base times height, so I'm basically going to say it's this quantity squared. Or if you really want to write it twice, go ahead. And now to find the volume of that figure, I'm just going to integrate the area that I wrote down. 4x minus x squared minus 2x squared dx. And of course I need to get bounds, and the bounds are where these two functions intersect. So I know my lower bound is 0, that was fairly obvious. I need to get that upper bound, so I'm going to set 2x equal to 4x minus x squared, where they intersect. I'm going to bring this over, so I've got x squared minus 2x equals 0, so I would say 0 and 2. And if I integrate this function, which I'm not going to do, I'm going to let my calculator do that part, I'm just going to set it up for the time being, I would find the volume of that figure when I put all those squares, an infinite amount of squares inside. So it's a pretty neat idea. There are actually lots of buildings that look like this. Let me give you an example of a building you may or may not be familiar with. Here's the Luxor Hotel out in Las Vegas. Like I said, you may or may not be familiar with it, but basically it's in the shape of a pyramid. And if you were to take a slice, if you were to cut that pyramid right in half, you would be staring at a square. And it's made up of an infinite amount of squares, and you could easily calculate the volume of this hotel. It's pretty fascinating. All right, we're going to take the same two functions, and I just resketched it for myself here on a new screen. And this time, instead of using squares, we're going to use rectangles as our slice analysis. Now, with rectangles, they have to give you another piece of information because clearly the base and the height are not equal. So they have to tell you something about one of them. So, and it changes in every problem, you just have to read carefully. I'm going to say the height is 3 times the base. Okay, and that's not a rule of thumb. Like I said, it's going to change in every problem, so just read carefully. All right, so you do want to show on paper slice analysis. All right, that's something we're going to be looking for on the AP there. So again, and take some notes off to the side yourself. On a slice analysis, you're basically going to find the area of one shape, and then you're going to integrate it to find all of the area added up to get the volume. So I always start with the formula of the shape I'm finding. Rectangle is base times height. So they're saying the height is 3 times the base. So I'm going to start with my base. I am going to rest my rectangle right on here. So I'm going to say it's my green curve minus my red curve. Now, something we haven't talked about before, you can shorten them up a little. I believe I called the green curve g of x, and I called the red curve f of x. It's fair game, and they'll take this if you just want to say g of x minus f of x instead of writing the actual functions in there. Okay, I can just say g of x minus f of x. Now the height. Go back to that rule. The height is, so that's h equals 3 times base. So I'm going to say that's 3 times g of x minus f of x. All right, now you just need the area. Area formula you jotted down was base times height. So if you take this base and multiply it by this height, I'm going to have 3 times g of x minus f of x times g of x minus f of x. Or I could just say that's 3 times g of x minus f of x squared. Therefore, the volume of this figure with rectangles, whose height is 3 times the base, is the integral, we said from 0 to 2, of 3 times g of x minus f of x squared dx. And there you have it. All right, I want to do one more shape. And you'll notice, just throwing this idea out there, some people use the BHAV, I don't know, however you want to say it, as the acronym they use. You always need a base, a height, an area, and a volume. Just a little tidbit there. All right, so I'm going to use the same picture and set up one last problem with semicircles. Now, this setup is just a tad bit different because it's not the same area equals base times height idea. So be very careful with the semicircles. Now, when you say semicircle, what pops in your head? Well, hopefully you're thinking the area formula is 1/2 pi r squared. Okay, so no base times height this time, it's 1/2 pi r squared. Now, I want you to picture a semicircle in here, so let's kind of make a quick sketch. Semicircle is obviously half a circle, and I'm just going to draw it off to the side. I'm looking at this, half a circle. And if I picture that coming out at me, this distance here, this base, so to speak, is actually the what of the circle. Would you say that's the radius? I hope not. Hopefully you're thinking that's the diameter of the circle. So in my slice analysis, that's actually what I'm going to start with. I'm going to start with diameter and say that is my g of x minus f of x. And then I'm going to say, okay, the radius is half of g of x minus f of x. And now I need the area formula. Area equals 1/2 pi radius squared. So be careful, you're taking this term and you're squaring it. Well, if the 1/2 wasn't there, it would just be g of x minus f of x squared. But since the 1/2 is there, you're actually getting 1/4 g of x minus f of x squared. And if you clean that up, you are now actually getting 1/8 pi g of x minus f of x squared. So the volume, if I wanted to fill that shape up with semicircles, I'm going to pull out the 1/8 pi, still integrating from 0 to 2, of g of x minus f of x squared dx. So if I went too fast for you, take your time, pause it, rewind it, make sure you can understand where that came from. All right, and it's all about that area formula there. And just remember that this distance is actually the diameter. Then you needed your radius, which was half of that. Radius squared became 1/4. Still, it's 1/2 because it's half a circle, and we get our 1/8. All right, I really want you to pause it, try it on your own. Here are your two functions. We're going to do 3 slice analyses. We're going to do the square. I'll give you a rectangle rule and a semicircle. So first and foremost, you obviously have to be able to sketch these graphs without a calculator. I think the e to the x graph is probably the easiest. We should know what that looks like. This is just shifting you down 5. So remember, e to the x normally crosses at 0, 1, and if you shift that down 5, think about where you're going to be. We know what x cubed looks like, I would hope. This is shifting you right 1. Okay. Hopefully you've got your area between those two curves. And just to make this go a little quicker, let's just, for the sake of it, call that intersection point A and that intersection point B. I don't even want you to find them. I'm just going to focus on the setups here. So your first slice analysis will be a square. All right, so like I said, pause it, try it on your own, see if we get the same thing. Go for it. So hopefully you were honest with yourself, you've paused it. I've got my base as f of x minus g of x, upper minus lower. Because it's a square, I either said side squared or base times height. Obviously it's the same thing. So my area is that quantity squared, and my volume, if I were to fill that with squares, is from a to b of that function squared. All right, I want you to do the same thing this time. I'm just going to change that square now, and let's call it a rectangle. And remember, they have to give you a rule for a rectangle. And I'm going to say the height is the square root of the base. The height is the square root of the base. So same picture, look in your notes there and go ahead and set up a slice analysis to find the volume. Pause it, be honest with yourself, and try it on your own. All right, see if mine matched yours. I said the area of my rectangle, of course, and I'll just draw it out here, is base times height. So I said it's upper minus lower, so that's f of x minus g of x. My height was the square root of whatever my base was. So I said the square root of f of x minus g of x. Then I said my area, and you can check my math here. If I have f of x minus g of x to the first times f of x minus g of x to the 1/2, when you multiply, you add the exponent, so I got f of x minus g of x to the 3/2. And then to find the volume, I just integrated that function. Notice, the one thing I'm not doing is I'm not throwing any pi's on here. Unlike rotating when we did pi r squared, those all had pi's. We're not rotating anything, so please no pi's. All right, lastly, same functions, and let's go semicircles. Okay, so again, don't cheat yourself, pause it, see if you can nail this one on your own. All right, here's my slice analysis for the semicircle. And another thing you might notice me do is I like to draw out the shape, and it just helps me identify who I have. For example, with semicircle, I need to be starting with a diameter of a circle. So I said pi r squared, here's my slice analysis. Diameter was my upper minus lower, f of x minus g of x. Now it's just common sense from here. A radius is half of the diameter, so that's why I have 1/2 f of x minus g of x. The area formula is 1/2 pi radius squared. So the 1/2 turned into a 1/4, and this junk squared. And then to get my volume, I said, okay, I'm just going to integrate whatever I wrote for area. And you'll notice I have 1/8 this time because I have 1/2 times a 4th, so that's 1/8 pi f of x minus g of x squared from a to b dx. Now, of course, you could pull the 1/8 pi out front. And, take notice that this is the only one that has a pi in it for slice analysis. Well, there you have it. We've talked about 3 slice analysis today, and we'll talk about a few more tomorrow. Have a great night, and we look forward to seeing you back.